Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the first Corrosion Center webinar series. The Corrosion Center is part of Qatar Environment and Energy Research Institute that is part of Hamad bin Khalifa University and also is one of the RDI research centers that are associated with Qatar Foundation. We will be talking today, this is our first corrosion webinar, and we will be talking about corrosion of concrete structures today. And first, I would like to give just a brief introduction of who we are, because I realize that there are a lot of attendance in this. There is a lot of attendance in this webinar, and we have a lot of international attendees. So QEERI is a national research, development, and innovation RDI institute, and we focus mostly in water, energy, and environment in arid regions. However, we go even beyond. We are specialized in R&D, RDI, research, development, and innovation. And under QEERI, there are several centers, research centers, and one is the Corrosion Center. The Corrosion Center has been established in September 2019, so we're still new. We have different area of interest, and as you can see here, this is our area of interest, and big part of our interest is corrosion solutions and corrosion management. And this is where concrete corrosion comes in as one of our important area of interest that we are trying to build capacity in Qatar to work in, and at the same time, we're trying to support the Qatar in monitoring infrastructures. So today in this webinar, we have 4 of us that are included in this. So my name is Hanan Farhat, and I'm the Senior Research Director of QEERI's Corrosion Center. And with me, there will be Professor Mariano, and he's the Curtin Corrosion Center Director. And Mariano will talk about the QEERI Curtin Corrosion Center Alliance that we just established in March. Then we have Professor Warren Green. Professor Warren Green is visiting adjunct professor at Curtin University. He will be our speaker today. Dr. Green has over 30 years of experience in materials and corrosion engineering. He's specialized in covering infrastructure, civil structures, buildings, marine. So we will hear a lot about his experience, and I'm quite sure you will enjoy this webinar. And then we have Dr. Mobin. Mobin is helping us in moderating this webinar. I'll be the moderator. Mobin will be supporting me with the Q&A. We have in the background, we have Ms. Dilraz. She's our communication at QEERI. She's our communication specialist at QEERI, and she's the one who's organized the whole webinar that you're seeing. So the invitations, the links, all these communications we've been receiving, she's been working on. So she's working in the background. You're not going to be able to see her today. I will give you just some of the guidelines for this webinar that we need to follow. So number one is that all of you can notice that your microphones were muted. So we're trying to reduce the noise and give only the chance to the speaker to talk in here. So if you need to unmute your microphone, this has to be done through the host. And if you have any questions to ask, so please, we encourage you to put your questions in the Q&A window, and we will aim to answer as many questions as possible at the end of this webinar. The webinar is being recorded, so if you miss part of the webinar, you can always watch it at HBKU video portal. If you're posting anything about this event in social media, please use hashtag QEERI webinar. The session will last for 1 hour. Warren will be talking, having 40-minute talk, and then followed by Q&As. If you want to manage your view, please click on the buttons that are provided in the screen. I will leave the floor now to Warren to start his presentation, and then we'll come back when we have the Q&A session. Thank you.
Thank you, Hanan. And Mariano was going to first say a few words in relation to the QEERI Curtin Alliance in corrosion. So before I start my presentation.
So just want to show one slide about the Corrosion Center. So welcome and thanks everyone for joining our first webinar. For everyone that wants to learn more about the Curtin Corrosion Center, because I think it's best use of our time to let Warren use the time for his presentation. Just go to our website at curtin-corrosion-center.com, and you will see you have more information about the history of the center, the research expertise and research capabilities of the center. Very briefly, Curtin Corrosion Center has been at Curtin University for over 30 years. It was founded by Professor Brian Kinsella, who is an emeritus professor. He retired last year. I'm the director of the center. We are about a group of 30 researchers, including students, PhD students, working on different areas of corrosion and material science. Primarily do research for petroleum mining industries. We have worked some projects with the defense and chemical processes industries as well, and we cover a broad range of corrosion expertise, from environmental cracking to microbial corrosion, corrosion inhibitors, coatings, and so on. We are located in Perth. Let me put here my laser pointer. So Perth is located in the west side of Australia, so it's the other end. All the other big cities are on the other side of the country. Yeah, and Curtin University within Australia is one of the largest. I think it's the 7th largest university in the country. Together with Dr. Hanan, we signed, we are honored to have signed this agreement in March 2020. It's an alliance on corrosion and material science research. And our idea, our work, is to join forces to tackle recurrent and costly corrosion challenges, particularly in the oil and gas industry. And there are several synergisms between the problems that we face in Australia to those that you face in Qatar. And we are going to be combining our expertise to address 4 themes within the alliance. Acid gas corrosion is led by Dr. Moin Selassie, and Moin is with us today. Corrosion under insulation is another of our main themes. Coating degradation and coating performance, and microbial influence corrosion. Currently, we have, or the Alliance will have 3 senior researchers assigned full-time to work on these themes. Currently, we're hiring 2 new postdocs for the Alliance, and we are trying to fill 4 PhD positions. In addition to that, we have several subject matter experts from Australia, from QEERI, and from NTNU in Norway. Warren, that's all I had, so I will pass it back to you.
Thank you. So welcome everyone. It's a pleasure to be with you, ladies and gentlemen, to talk about this subject of corrosion of reinforced concrete structures. Imagine the world without reinforced concrete structures. They are numerous, and that's deservedly so, because it's such a versatile material, composite material, and we expect a lot of our concrete structures, so they deteriorate. So what I thought we'd cover in terms of topics is that we'll just begin with some of the key characteristics relating to steel reinforced concrete. We put the steel in the concrete to provide tensile and shear strength to the composite material. But the concrete provides wonderful corrosion protection to the steel reinforcement. So we'll go over the relevant aspects there. By far the biggest form of deterioration of the concrete is the steel reinforcement corrosion. So We'll go over some key issues in relation to that. We can investigate and diagnose concrete structures to find out what's wrong with them and where there are problems. So we'll go over survey and diagnosis. We can repair and protect them. So we'll go over some key issues there. And then we can prevent and make our new reinforced concrete structures more durable. So we'll touch upon that as well. So in terms of a starting point, why do we incorporate steel into concrete? Concrete is poor in strength in terms of tension and shear, so that's the principal reason for which we incorporate steel into the concrete. And the reinforced concrete itself's been around since the mid-19th century, so we've got good sound experience with its use. So in terms of the key components of concrete itself, we have inert mineral filler, so we have coarse and fine aggregate in the concrete, and then we have a cement matrix, and we add water to the cement matrix. It hydrates and then binds the aggregate together to form the solid mix. Now, in terms of these aggregates that we use in concrete, we use siliceous-based aggregates and carbonaceous-based aggregates typically. And the other important aspect in terms of hardened concrete is that there are pores within the concrete. So capillary pores within the hardened cement paste of the concrete that allow aggressive agents to penetrate it and then compromise its performance. So we'll talk about aspects to do with those pores. So diagrammatically, we've got the, I'll just get the laser pointer. So we've got our coarse aggregate, our fine aggregate, and then it's bound together into a graded mix by the cement paste. So in terms of the cement that we commonly use for reinforced concrete is Portland cement. So and it's so named after the colour of the cement. The person that invented the cement in 1824, he lived near Portland in England, and what he developed in terms of the cement reminded him of the grey colour of the Portland stone, and so he named it Portland cement. So Portland cement is the most common cement that we have available to us, and it's manufactured by, you need specific oxides to manufacture Portland cement. So you need a source of calcium oxides, you need some silicon dioxide, aluminium oxide, some iron oxide, and then some other sort of trace oxide materials. Now we get those most commonly by heating a mixture of limestone and clay. In some countries, we get our source of silica from sea sand, and our calcium from limestone, and our aluminium oxides from bauxite. So Portland cement is nominally a mixture of these key oxides. Now, we mix those components into in a rotary kiln. We heat that kiln to a temperature of about 1500 degrees Celsius, and what comes out of the kiln is clinker. So they're like grey black pellets that are about the size of marbles. We take that clinker, we grind it with some gypsum to stop flash setting of the cement. We grind it with some gypsum, and there's some cement compounds that are formed because of the way we heated it and the temperature that we heated it at, and the way we heated it inside the kiln. So we finish up with key components that are silicate-based components. There's an aluminate-based component and an aluminoferrite component. So when we add water to these components, they react with the water, and they hydrate the cement phases. So we finished up with hydrated cement compounds. And a key component of the products of reaction of hydration of the cement is calcium hydroxide. And calcium hydroxide is given off as a product of reaction. So the pores of the hardened concrete are full of saturated calcium hydroxide, and that's important from a corrosion protection point of view. So here's diagrammatically cement paste. So we've got capillary pores, just a diagrammatic representation of cement paste. So we have pores. This is the hardened cement paste component of the concrete. We have capillary pores, and then we have gel pores as well. It's the capillary pores that concern us from the point of view of the durability of reinforced concrete. So we can incorporate mineral additions with the Portland cement component to make what's termed blended cements. So there's various mineral additions that we can add. And those mineral additions react with that free lime, so that calcium hydroxide, to form a supplementary cementitious material. So a supplementary cementitious material in addition to the Portland cement component. So we can incorporate blast furnace slag, fly ash, and silica fume are the most common mineral additions that are incorporated into concrete. So they produce blended cement-based concretes, and these mineral additions improve the durability of the concrete. So in terms of steel reinforcement, just to close out this first topic, we've put the steel reinforcement in the concrete to increase its tensile and shear strength. So short, we call it rebar. So there's conventional reinforcement. So here we've got the designations for Australia and New Zealand standards. But the same applies no matter where we are in the world. We've got standards for conventional rebar. Then we can use pre-stressing steel, so high tensile steel can be incorporated. So we can pre-tension concrete. We can post-tension concrete as well. We can also use other steel reinforcement in the concrete. So we can incorporate galvanized steel reinforcement. There are stainless steel reinforcing bars available to us, and there are metallic clad reinforcing bars as well. So a variety of steel reinforcement. We've also got steel fibers that can be incorporated as well. So we can incorporate galvanized steel. There's various grades of stainless steel or types of stainless steel that we can incorporate into the concrete, and then we got metallic clad reinforcement as well. So that was sort of it in terms of the key fundamentals relating to steel in concrete. Let's look at the protection afforded to the steel reinforcement by the concrete. We'll look at that. So the concrete provides excellent corrosion protection, and it does that in fundamentally three ways. So that calcium hydroxide, that was a product of cement hydration, means that we have a high alkalinity in the pore solution of the concrete. And that high alkalinity, when you place iron in high pH environment, it passivates. So at high pH, iron passivates, the steel passivates. We can make concrete a very low penetrability as well. And it's also got a relatively high resistivity. So we'll touch upon these aspects. So alkalinity-wise, with the capillary pores and the gel pores of the cement paste, the pH is 12 to 14. So the pH of saturated calcium hydroxide is about 13. Okay. So if we place iron, the steel in that environment, it passivates. And it will stay passive unless we cause acid to be formed at the metal surface to neutralize and deteriorate that passive film. So a lot of these slides that I'm showing tonight or today are from the concrete corrosion unit within the MSc at Curtin University. So you can do an online MSc, and therefore we should talk about electrochemistry as well. So we'll just have a few slides on electrochemistry. So the first is in terms of the thermodynamics. So Porbay has taught us that if we plot potential versus pH and we look at the conditions that were within concrete, then a Porbay diagram, thermodynamics tell us that iron will be passive, right? So thermodynamically at that pH, we get passivity. Kinetically, Evans diagrams help us in relation to that. So here we've got potential versus log of current. We place iron in a high pH environment. We get spontaneous formation of a passive film on the metal surface. The corrosion current here is directly related to corrosion rate, and the corrosion rate is low. So Cherry told us that. So the late Professor Brian Cherry from Monash said that if you put steel in good concrete, it's protected by a passive film. And simplistically, that passive film is gamma iron oxide. So maghemite is formed, right? And we've measured the corrosion rate of maghemite, and the corrosion rate is only 0.1 microamps per square centimetre. So that's a corrosion rate of 1 micron per year. So it's insignificant. Now that passive film maintains itself as well. So it self protects itself. It maintains a constant thickness, and so it doesn't set up any swelling pressures in the concrete. So in terms of the thickness of the passive film, it's thin, it's tenacious, it's highly protective, but its thickness is about 10 nanometers, 100 angstroms. So electrochemically, that's what happens when we put steel in concrete. We've also got it as a physical barrier as well. So we provide some cover, and it can take significant periods of time for aggressive agents to penetrate through the concrete, through the physical barrier. And then in terms of the resistivity of concrete, it's very high in relation to other environments. So it's many tens of thousands of ohms centimetre. Okay, so there's those various mechanisms of protection. So in terms of the corrosion of steel of reinforcement in concrete, there's various things that degrade it, right? There's mechanical degradation, there's physical degradation. We can structurally degrade it because we've got so many reinforced concrete structures in our world. It can be chemically attacked. So it can be chemically attacked internally. It can be attacked by inorganic salts. It can be attacked by acids, alkalis, and so on can attack its salt solutions. It can be attacked by biological, but by far the worst form of deterioration is corrosion of the steel reinforcement. Okay, and that occurs by various methods. So let's touch upon those. So all of those methods of corrosion of the steel reinforcement lead to loss of that passivity. So we can carbonate our concrete. Chlorides can cause corrosion, so our marine environments. We can leach the lime out of the concrete. Ground currents and interference currents can cause corrosion and loss of passivity. So we'll just quickly walk through these mechanisms of depassivation of the steel in the concrete. So carbonation, we've got more than 400 parts per million carbon dioxide gas in the atmosphere. It penetrates into the concrete, dissolves in the porous solution, and forms an acid, carbonic acid or weak acid. That acid reacts with the calcium hydroxide, the portlandite. That was a product of hydration of the cement. And we form calcium carbonate. Now what that does is the pH of the concrete reduces from 13 down to a pH of 9. So the passive film, that maghemite film, is only stable at pH levels of greater than 10. So we carbonate our concrete to 9, 8.5, the passive film is dissolved. Okay, and I'll go over how to measure the carbonation of concrete in a minute. So in terms of electrochemistry and corrosion reactions, for corrosion to occur, we need an anode, we need a cathode, we need a conducting link between the anode and cathode, and we need an electrolyte. Okay, so the carbonation penetrates through the concrete. When it dissolves the passive film, we get an anode, we get anodes established, we get oxidation reactions at anodes. The electrons that are produced by the oxidation of the iron to the ferrous ions associate with, in this case in the concrete, oxygen, dissolved oxygen and water to form hydroxyl ions. The circuit's completed by the ionic transport of the hydroxyl ions in the ferrous ions, and then we form different forms of corrosion product. So we'll talk about those forms of corrosion product as well. When it comes to chlorides, so that's for carbonation, chlorides, we get those from marine environments, we get them from in-ground saline environments, we get them from atmospheric exposure as well. So those chlorides in those environments penetrate, diffuse through the cover concrete, and when they arrive at the steel reinforcement in sufficient concentration, they initiate pitting corrosion of the steel in the concrete. So then, in terms of the corrosion reactions here, so the chlorides penetrate through the concrete, break down the passive film, punch holes in the passive film. We get an oxidation reaction at the anode. Secondary reactions the secondary reactions in terms of corrosion products. Cathodic reaction is oxygen reduction. In the case of chlorides, though, we get pits, and we get hydrolysis reactions occurring in those pits. So we generate within the pits. So here's a blown up pit. We generate acid in the pit, so we can measure pH. The measured pHs are down as low as 4 in terms of hydrochloric acid, right? So we get pitting corrosion. In terms of the corrosion products that are formed, they are more voluminous than the parent steel. So depending on the type of corrosion product, so if we've got black rust like magnetite, we get red rust hematite, or if the hematite's hydrated, it's significantly more voluminous than the pure iron. Okay, so what that does is that leads to tensile stresses set up in the cover concrete. So this is a reinforced concrete marine structure. We first of all see rust stains, cracks, and that expansive corrosion product causes the cover concrete to detach, to delaminate, and then when it falls off, it's called a spall. But we don't always see visible damage. So if you've got severe pitting corrosion, like here we can see some green rust, we can see significant section loss, and we see no visible signs. So you can actually lose locally reinforcement. So pitting corrosion, chloride-induced pitting corrosion, is our major concern, and we need to diagnose structures for that. So we can break down that passive film by leaching as well. So here on this example, these are water tanks. We can see the black rust running down this outside of this water tank. So the water is leaching through, penetrating through the joints and cracks, and lowering the pH such that you get corrosion locally of the reinforcement. Now, ground currents from our electrical traction systems can interfere as well, and big cathodic protection systems, so they lead to local reinforcement corrosion. So we have these problems with our structures. Can we diagnose them? Well, yes, we can. So we do a condition survey and we assess the condition of our structures, right? And that's generally divided into 3 stages. We do a visual inspection. We're able to do electrical and electrochemical on-site measurements. We're able to sample the concrete, we send it to laboratories, and we get it chemically analysed. So we do visual inspections by diligently recording deterioration to the concrete, cracks, spalls, rust stainings, and the like. We can measure the cover. So the amount of cover, protective cover to the reinforcement is important. So we can do that with cover meters, non-destructively on site. We can identify areas of corrosion activities by measuring the electrode potential. So the potential of the steel in the concrete. And we map those. We map the potential. We produce potential maps. So here, these red and orange areas are areas of corrosion when it comes to this reinforced concrete element. So we can identify the hot spots, find all the corrosion in our structures. And in these instances, the corrosion is not visible. This is hidden corrosion and potentially pitting corrosion that we need to diagnose. We can measure the resistivity of the concrete by our traditional 4-probe method, soil resistance measures. Right, take a soil resistance meter and measure the resistivity of the concrete. We can measure corrosion rate of the steel in the concrete. The most common way is polarization resistance from Stern and QEERI in the mid-50s. So we use polarization resistance. We can identify cracks, voids, and so on with ultrasonic pulse velocity measurements, for example. We can get cross-sectional images of the concrete with pulse echo. We can identify voids and delaminations and the distance to the defect with impact etho methods. And we can transmit radio waves through the concrete to detect voids and delaminations, the depth of defects, locate the steel reinforcement, and so on. So there's various electrical and electrochemical methods that we can apply to our reinforced concrete structures. So while we're on site investigating the structures, we can measure the depth of carbonation. So here we use phenolphthalein pH indicator solution, and we spray it onto the concrete surface. Okay, so we've broken this concrete out here. This pink purple area has a pH of 13. That's not carbonated, that's uncarbonated, right? But here on the surface, you can see that there's a colourless depth, and that's the depth of carbonation. So the CO2 is penetrating the concrete, dissolving in the pore water, neutralising the calcium hydroxide, sodium and potassium hydroxides, and lowering the pH. So it penetrates in as a front. We can sample the concrete by wet diamond coring. We can drill and collect concrete dust. And those sampling, from that sampling, we send it to laboratories to enable us to do measurements. Right? So we can assess the concrete quality. We can measure the depth of chloride penetration, sulfate content, and so on. So in terms of the depth of chloride penetration, we've taken our cores and drillings. We do that at various depths. Then we analyse it, we dissolve the sample, and we measure the amount of chloride. So the chloride from diffusion, you get a high concentration at the surface, reducing with depth into the concrete. Sulfate analysis is done typically gravimetrically, so we can measure the amount of sulfate, remembering we've got gypsum already in the cement. We can do petrographic examination to identify various forms of deterioration, and we can use more sophisticated laboratory testing for inorganic and organic scanning electron microscopy and so on. Methods can be utilised as well. So those laboratory methods are necessary as part of the conditions survey. Now, in terms of the repair and protection of our reinforced concrete structures, we've got options available to us. In the life of a structure, there's a period of time to initiate corrosion, and then there's a period of time where the corrosion propagates. So what that means is that we've got options available to us to prevent corrosion initiation, to slow corrosion, and to stop corrosion, whether the corrosion be from carbonation or whether it be from chloride attack. So we'll just talk about a few of those more common methods of repair and protection. We can patch repair our concrete. So we break out our concrete and we can reinstate it with various proprietary construction material supplier materials. So we can hand apply it like here. We can spray it, and we can form and pour it. So sprayed concrete repair is called shotcrete or gunite. So we can spray repair. There are inhibitors available that we can apply to the concrete or incorporate in the concrete. Inorganic and organic inhibitors. We can coat the concrete. We can do that with coating systems. We can also do it with silicon-based materials, so silanes, siloxanes, silicones, and the like. We can cathodically protect concrete. We can do it by both impressed current and also galvanic means. So there's quite a range of concrete impressed current anode types that are available. We've got ones that we can put on the surface of the concrete. We've got anode systems that we can encapsulate, and then we've got anode systems that we can put in for the immersed sections of our structures or the buried sections. So we've got anode types available to enable us to do targeted impressed current cathodic protection. We can galvanically protect. We can apply galvanic anodes to concrete. Here we don't have obviously have a DC power source, so we don't have a transformer rectifier unit. We're just relying on the potential difference between the anode and the rebar to cause the current to flow. So what are those type of anodes? We can spray. We've got to spray more electronegative metals onto the concrete or encapsulate them in the concrete. So we use zinc and we use aluminium alloys. So we can put it on the surface. We can put those metals on the surface. We can encapsulate zinc in different forms, and we can use our traditional galvanic anode cathodic protection for our immersed and buried section. So we can install cathodic protection in new structures as well. So here you use ribbon or mesh, and you do this where the applicable corrosion risk is very severe, or we want a very long design life. So we don't apply cathodic prevention necessarily over all our structure. We just apply it where we need it, where the corrosion risk is greatest. We can pull chlorides out of concrete electrochemically. So we apply a temporary impressed current cathodic protection system. Chlorides are negatively charged. They get drawn towards the positively charged anode on the surface of the concrete. We can realkalize concrete. So in the case of carbonated concrete, we can regenerate the passive film. We can restore alkalinity. And again, this is just a temporary impressed current cathodic protection system. We can strengthen concrete with fibre reinforced polymer materials, laminates and wraps. We can stick steel plates on and so on. So we can selectively strengthen elements of our structures as well. Now, just in terms of finishing up here, we've also got options available to us to prevent deterioration and corrosion in our concrete. So improve the durability of the concrete. So I'll just touch upon those just to sort of finish things off in terms of this webinar. So we can improve concrete durability with concrete mix design. We've got various admixtures available to us that improve the concrete. We've got coatings and penetrants. We can use alternate reinforcement, and we can have intelligent structures where we put permanent corrosion monitoring. So we've got options available to us in terms of concrete mix design. We've got different cement types. We can vary aggregate, vary water content to make the concrete more durable. We've got a variety of admixtures that enable us to constitute the concrete, compact it, cure it, and place it, and so on. So we need admixtures to enable us to do that. We can coat the concrete, so we can put coatings on it to stop carbonation. We can put coatings on it to stop chloride penetration. We can treat it with penetrant-based systems. There's elastomeric coatings. We can have textured coatings, membranes, and so on. So these are inorganic and organic materials. They've only got finite lives, but we can protect our structures if we need to. And then we've got options in terms of alternate reinforcement. So we can galvanise steel. So galvanized steel. So zinc is a passive metal as well. And it takes approximately twice the amount of chloride than carbon steel to corrode it. So we can prevent the onset of chloride-induced corrosion. Zinc's an amphoteric metal. So at pH 9, it remains passive. So it's passive against carbonation. We've got various grades and types of stainless steel reinforcement. And we've got the austenitic, we've got lean duplex, duplex, and super duplex. So these have a much higher chloride resistance. So the amount of chloride that to break down the passive film on the stainless steel is potentially up to 10 times higher. So we can use stainless steel selectively. We don't need to put it in all our structure. We just put it where the critical areas are. Obviously, stainless steel is more expensive than carbon steel, so life cycle costing is often done. There's fibre reinforced polymer reinforcement available to us as well. So we've got aramid and carbon and glass fibre, and we can permanently monitor our structures. So there's various probes, sensors, and so on that have been developed that we can put in critical areas of the structures or in areas that are inaccessible, and we can monitor the ingress. So this probe, for example, a ladder probe here, angled in the cover concrete. As the chlorides come in, you know they initiate corrosion of these rungs of the ladder, and you know where they are, or you know where the carbonation is. So you can take preventative action if you need to. So, ladies and gentlemen, that was a whistle-stop tour through various aspects to do with corrosion of reinforced concrete structures. So I hope that you got something out of that. So thank you, ladies and gentlemen.
Thank you very much, Warren. Hanan, we cannot hear you. I don't know if you want to. Now I can hear you.
Yes. Thank you very much, Warren. Very, very interesting presentation, and I guess you covered all the aspects of the corrosion of reinforced concrete structures. We received several questions in the Q&A section, so I'm going to be asking you some of these questions, and we'll try to answer as many as we can today, but minding the time of the webinar as well. So the first question was about asking how the lifetime of steel in concrete structures. They meant that the corrosion rate changes as a function of chloride concentration.
it does change. So the higher the chloride concentration, the higher the corrosion rate. But the corrosion rate's also impacted by the quality of the concrete. So we can make very high strength, very high quality concrete where the corrosion rate can be quite low. So it varies. It varies.
So I guess the higher the chloride content is, always the higher the corrosion rate.
Yeah, that's right. That's right. And it's the chloride content at the reinforcement depth. Yeah.
Another question is someone is asking: do we need to install new probes for mapping the concrete?
You can put them in important structures. So it's not uncommon now to design reinforced concrete structures, bridge structures and the like, for 100-year design life. Some bridges are 300-year design lives. Obviously, nuclear and other structures is even more than that. So you can put reference electrodes and other probes in critical or inaccessible areas, and yeah.
Okay, we got a question asking about epoxy coating. The question says, can we use epoxy coating when we have ICCP?
No. So it's isolated. Your reinforcement isn't continuous, and the problem with epoxy coated rebar is when it becomes compromised, you get local corrosion, pitting corrosion, and it's difficult to diagnose, and you can't get cathodic protection onto epoxy coated rebar because it's electrically isolated.
Is there a way you can use wireless sensors to monitor concrete structures?
The sensors that are being developed and the work that's being done in that area, there are wireless. Yes, definitely wireless sensors available.
This question is a bit tricky. I don't know if you will get it. It says how possible it is to fix initial stage of a not visible pitting corrosion inside the concrete.
You need to first diagnose where the pitting corrosion is, and then depending on the element type, if we just take an example that it might be a pre-stressed beams in the substructure of a marine, of a wharf, we diagnose where the pitting corrosion is, and then the options that we have available to us are the options of stopping corrosion. So we can break the concrete out and we can patch repair it, or we can apply cathodic protection. They're the only methods to stop the corrosion. So if we want to stop the corrosion, the only method we can use is impressed current cathodic protection, and we apply it where we need it. We don't necessarily need to apply it widespread over the structure, because it may not be economic to do concrete repair. The amount of concrete repair may be too extensive.
Warren, I know that you have experience in the Middle East with concrete structures and corrosion of concrete structure. Could you please give us a little bit of, a summary of what you had?
It was a number of years ago, and then we with QEERI, we're from a Curtin University point of view, we're looking at other opportunities in terms of Qatar. But the elevated temperatures that you have, the higher salinity levels, the aggressive ground conditions, and so on are unique to your countries, and so the corrosion of steel in the concrete is more aggressive. I mean, in our country here in Australia, in our north of our country, and so on the coast, we have very aggressive conditions, but not as aggressive as the Middle East. Yes.
So do you propose, like for concrete structures in the Middle East, to have a protection plan like ICCP from the beginning, or just choose a better material, which is going to be expensive, like looks like stainless steels?
Yeah, well, their cathodic prevention is certainly an option, Hanan. And you may need to consider selective use of alternate metallic reinforcement. But focus could be had on improving the quality of the concrete. So we've got various options available to us, even in elevated chloride levels, to provide good durability to the steel in the concrete. And the experience, as an example of where that experience we can draw upon, is, for example, in desalination plants, where we have hypersaline conditions, and we have reinforced concrete structures for those desalination plants elements.
So Warren, maybe Hanan, I can take. I've seen a few questions that are coming all around the stainless steels.
Yeah.
And Warren, the question is, if you select the stainless steels, are you concerned about pitting corrosion and how you deal with it? And one related question to that is whether hydrogen embrittlement could be a problem when you have impressed currents.
So to answer the first question, Mariano, yes, pitting corrosion is the risk we must manage, and depending on the alloy type, is the pitting resistance of our stainless steel. Now, stainless steel rebars like to be at high pH, like iron based bars do. So we've got that advantage. So we could choose a grade of stainless steel and alloy type that doesn't pit. And hydrogen embrittlement is something that we must manage when it comes to cathodic protection of stainless steel. Yeah. So we can't overprotect it. We can't generate atomic hydrogen on the metal surface.
Okay. Warren, there is a question about the efficiency of saline and siloxane. Sorry.
Silane and siloxanes. Mm.
Yes. The efficiency of coatings.
Yeah, well, they're penetrant-based systems, so they don't form a film on the concrete surface. They rely on their protection by making the concrete hydrophobic. So the surface tension of the water, or the chloride-contaminated water, is affected. So they don't perform under any head pressure. So if you apply any head pressure to silane or siloxane treated concrete, they won't have any effect. But they do perform when the concrete is wet and dry. So like splash zones and so on, they're an option, but you can't use them in tidal zones and so on.
How about their cost and durability?
Their cost?
Yeah.
I don't know what their current costs are. Yeah. In terms of their durability, they're still organic-based materials. So even though they penetrate the concrete, they've got a finite life. So the sort of life of a silane siloxane, depending on the type, would probably be of the order of 20 or 30 years. So you have to reapply them, like coatings.
Okay.
Yeah. So they become a maintenance item. Mm.
Okay. So the maintenance is an issue, yeah.
Yeah.
Another question about the minimum penetration levels in steel that is in concrete structures that are subsea structures. So like pipelines and structures that have steel associated with it.
So we have design codes typically that we work to, so that the more durability that you want out of your structure, the more cover that you give to your reinforcement. but there's a limit to the amount of cover that you can give from a structural point of view. So you may provide something like, up to 75 millimeters of cover. So you can vary the cover, Hanan, depending on the environment and the design life.
Okay. There is a question about galvanized steel. Is it okay to galvanize stainless steel such as 316 stainless steel, giving the problem of embrittlement? I guess giving the problem of embrittlement.
You wouldn't galvanize stainless steel, would you?
Oh.
No.
Oh.
No. But maybe that question is also related to whether there's potentially galvanic corrosion concerns between stainless steel connected to conventional carbon steel. Okay.
Yeah.
So when those steels are connected together in fresh concrete, both the metals are passive. So there's no galvanic issue, right, when they're passive. When the chlorides penetrate through the cover concrete and initiate corrosion of the carbon steel, because we know that the stainless steel has a higher corrosion resistance, higher pitting resistance, then there's a galvanic couple set up. But the research that's been done in relation to coupled reinforcement stainless steel and carbon steel is the stainless steel is a very poor cathode. It's a much poorer cathode than passive carbon steel reinforcement, in fact. So the coupling of the rebars doesn't exacerbate in terms of galvanic corrosion in concrete. Yeah.
Yeah.
Because of the cathodic reaction.
There's a question, Warren, about some structures in Qatar. We have structures that are built in the shore, like the Pearl, Qatar, and Lusail. And the question is asking about how do you see the concrete corrosion in the foundation of the high buildings in the new cities of Qatar, like Pearl and Lusail, due to seawater intrusion and to the shores? Is it a chronic problem, or there are solutions such as new construction material resisting formation of such thick layers of calcite or similar material causing deterioration of the buildings?
It's certainly something you have to design for structures that are in ground that are coastal. So we have to design for that. So we've got options available to us to make the concrete more durable. We've got options available to us in terms of the reinforcement type. If it's an existing structure, typically these structures deteriorate at joints, cracks in the structure, and so on. That those local areas and the saline water, groundwater, penetrates through the concrete and then leads to local corrosion. So we need to locally investigate, repair, and then maintain those areas. So sometimes that repair might be that you repair from the inside, or if you've got access to the soil side, the ground side of the structure, you could install cathodic protection, install anodes in the ground, and do semi-remote cathodic protection.
Okay.
So there's various options available, Hanan, there. Yeah. Depends how early you get it in the life of the structure. Yeah.
Yeah. Yeah. And I think, I don't know, but I think these structures is something maybe when we're considering our concrete corrosion research, maybe these structures will be something that we would look at and investigate.
Yeah. And then you can do a
question.
condition survey on them, yes, and you can sample them.
Yes.
We can do measurements to identify where they're corroding.
Yeah.
And any of that, like that person's question about the calcite, which is the calcium hydroxide that reacts with the CO2 in the air, you see lime depositing down the inside of these car parks. And if that lime's chloride contaminated, then you're going to get you're going to get local corrosion, aren't you?
Yeah.
Yeah.
There's a question asking in common textbook on good practices to prepare steel reinforced concrete, it's recommended to not use the fresh steel, but leave it corrode, which have a protective layer before pouring the concrete, thus increasing adhesion between concrete and steel. What about long term?
You probably shouldn't let a bit of flash rusting on the reinforcement is fine, but you can't let the reinforcement corrode such that you have lamellar type general uniform corrosion of the reinforcement, because the passive film does not form on the metal surface. So we can only have flush rusting, and that passive film, the maghemite, forms beneath the flash rusting on the metal surface. So a bit of flash rusting is fine, and that person's question in terms of bond is correct. That flash rusted rebar has in fact a better adhesion strength than bond strength than what very clean rebar has. Yeah, but you don't let it corrode too much. You don't want it heavily corroded when it goes into the concrete. Yeah, defeats the purpose really of putting it in there in the first place.
Another question about about silica. So there is a question about microsilica. It's asking how silica fume helps to prevent corrosion and reinforced concrete structures.
Right. Okay. So depending on, well, it doesn't matter. Well, the microsilica might be natural, or we might be getting it from our silicon smelters as a byproduct. It's silicate based. So it reacts with the calcium hydroxide to form calcium silicates, and those calcium silicates make the concrete less penetrable. So those capillary pores get filled with silica fume-based supplementary cementitious materials. So the primary purpose of the silica fume is to lower the penetrability, make it less permeable of the cover concrete.
Questions keep on going. Mariano, maybe you can take some of the questions.
Yeah, I think there is a general question, but maybe this can summarize the entire presentation, Warren. What is the most convenient way to stop corrosion of concrete? Is there one?
An existing structure?
I would guess so. It's not specified in the question, but
yeah,
let's assume so.
You've got there's only two options to stop corrosion in a structure. Is to replace all the contaminated concrete. So you break it all out, and you put fresh concrete or mortar back in and repassivate the steel. And the only other way to do it, so that could be too extensive and too expensive and impractical, because you might have to prop the structure, you might have to take loads off the structure and so on, right? So you can't just go berserk and break out and repair. The only other way to do it, regardless of the chloride content in the concrete, is impressed current cathodic protection.
There is another question about VCI, volatile corrosion inhibitors, if they're used in concrete structures. So someone is asking.
They are, and they're organic-based systems. The chemistry is proprietary, but you can topically apply. So they are commonly called migratory corrosion inhibitors. So you apply them to the surface of the concrete, and they penetrate, typically by diffusion, to the reinforcement surface. They're mixed inhibitors, so they impact the anodic reaction, and the cathodic reaction is the claimed way that they reduce corrosion. Their performance is somewhat topical is not the right choice of word. Contentious. Their performance is contentious. Yeah.
Okay,
But you can monitor Hanan. So just to finish that, you could monitor their performance. Yeah. You could monitor corrosion rate. So we can find out what effect they have on pitting corrosion and so on. We can measure polarization resistance. We can do impedance. We can do electrochemical noise. We can do all those electrochemical methods that we apply in other industries. We can apply to reinforced concrete structures, and we could assess the performance of the migratory corrosion inhibitors and see how much they reduce the corrosion rate.
Yeah. I think we're running out of time. We're at 12:15, and I think we should end this in 5 minutes. So I'm going to take just a few questions. And Warren, will you be able to answer the rest of the questions that we couldn't answer? We can maybe send them to the attendees. There is 36. Well, there is 68 questions in total on this. So we've answered some, but there are a lot that we still didn't answer.
Yeah. Well, we should be able to, shouldn't we? And then we'll just email you back or something, if they can just allow me a little bit of time to get back. Yeah.
Yeah. So there's one question asking about the most challenging issues in reinforced concrete structures that you see that they present in the industry.
I think the most challenging issue is in relation to pre-stressed concrete structures, in our ability to diagnose those, so identify where the pitting corrosion is, because we don't see damage to those structures. The corrosion is, because it is pitting, we don't see cracking, we don't see delamination, we don't see spalling of the concrete cover necessarily. Okay. So we've got to diagnose those very carefully. And the consequences of that corrosion of those pre-stressed structures is dramatic, in that they will just fail, brittly fail. So they won't yield, they'll just fail. And that's the concern. The biggest concern that I have is that our pre-stressed concrete structures are getting to an age where they're going to start to corrode. And we're not going to know it visually. With conventional reinforcement, we can see the damage, typically, but not with pre-stress.
Yeah. And what would be the consequences of such incidents?
Well, I think there's serious consequences, potentially. We just haven't necessarily seen them. We've certainly seen it in reinforced concrete in terms of local corrosion. So pitting corrosion. So the bridge in Italy, Berlin Congress Hall was pre-stressed concrete. Bridges that are failing, that are existing concrete structures, are failing because of local corrosion at joints, cracks, and so on. And so they're fine, and then they get loaded and they fail. So that'll be the same for pre-stressed.
Yeah. I think we like on this. Warren, do you want to say something at the end? You know, we finish off this. Do you want to summarize?
Hanan, I think there is a good question to help Warren summarize. I think the last one. Can you retrofit monitoring solutions to existing infrastructure?
You can. Yes. So we have various options available to us there. We have electrodes and sensors that can measure the corrosion and measure the corrosion rate. So we can retrofit, and we can have intelligent structures, and we can therefore assess the effect of the treatments that we do to those structures as well by making them intelligent. And some of our structures, Mariano, they're inaccessible. So tunnels, substructure elements of like, for example, the car parks that we were talking about there, the Pearl and so on. You could retrofit electrodes and probes to tell you what's happening with that structure and those elements in that structure.
Well, thank you, Warren, and thank you everyone for attending. We got a good attendance today, and thank you all the panelists, and thank you Delraz for helping organizing this webinar. We hope you can join us in the next coming webinars. We will be sending a schedule in the next week, so just stay tuned. We will email you back, all of you, with the answers to the questions that Warren wasn't able to answer today. Thank you all and have a good day.